Maria Stone, and this is part of the project Rainbows. Let's talk about Redshift because I'm going through and doing a lot of technical tutorials, and I wrote up some of the reasoning about the quasar spectra and limits regarding Redshift. So, in there are many things to talk about Redshift, or how the spectrum of object changes from what it is emitted to when we get the photons here, when we observe. But this is one of the concepts, the redshift. It is defined as a unitless quantity, and it is in a way a measure of the difference between observed wavelengths and wavelengths at rest. If you have, where's my little icon? For example, this is a theoretical um, spectrum where you have an emission line. For example, an emission line around 5,000 angstrom. Actually, yeah. Um, then at its rest frame, it is emitted from that object at z wavelengths. However, it is observed at a different wavelength, and we have to calculate to understand how far is the object. It's one way to measure the distance. So lambda rest is a wavelength measurement in rest frame. What it means is it is what was the wavelength of that emission line when it was emitted by that object. And lambda observed is a wavelength that we observe with our instrument. All right. And the redshift gets higher. This difference between observed and rest frame wavelengths gets larger the more distant an object is from us, because galaxies are, the universe we think is expanding, and galaxies are going further and further away. All right. For my quasars, in the sample of the Dusty Quasar project I'm working on right now, the redshift is constrained between 0.1 and 0.5. So I want to derive from this definition of redshift, I want to derive the formula for the observed wavelength. So for example, then we can determine what it is for H alpha prominent emission line with its rest frame wavelengths at 6585 angstroms, or about 6600 angstroms. So if this is the original formula, we can carry over lambda r. Then we can add a lambda r on both sides of this equation. And here they cancel each other out because there is a plus and a minus. We're left with z times lambda r plus lambda r equals to lambda naught. And we can group it because lambda r is a common term, so lambda r goes outside of a parenthesis, and inside we get just z plus 1, redshift plus 1. So we invert it for niceness, and we have our derived formula for the observed wavelengths, which is lambda naught. Lambda observed equals to lambda r times 1 plus z in parentheses. So in our case, redshift is 0.5. And for H alpha, the rest frame wavelength is 6600 angstroms. So if we plug these values in, we get 60 lambda observed for this H alpha is 6600 angstroms times 0.5 plus 1 times 1.5, which means if you're calculating in your head that you have the whole value and half of the value, So lambda observed is about 9,900 angstroms. It's almost 10,000 angstroms. It used to be 6,600 angstroms alpha. But now at this redshift, it's 10,000 angstroms, and it is equivalent to 1 micrometer almost. So it's a very large shift already at redshift 0.5. So it constrains how much we can observe, at least in the optical. Remember, the optical regime is a short window compared to the rest of the wavelengths, electromagnetic spectrum. Um, so the difference that it shifted is 3,500 about angstroms. So actually, it is beyond the GRISM capability of the NOT telescope, which I used, and it couldn't be observed. The GRISM was GRISM number 7 of the NOT telescope with alphosk. So that's why, you know, I used this information in order to plan which GRISM to use. The GRISM number 7 for alphosk at Nordic Optical Telescope can observe between these two wavelengths. This is the range from about 4,000 to about 7,000 angstroms. So 10,000 is um, way bigger than what can be observed. All right, with that GRISM. But let's check other emission lines, known emission lines for quasars. There's a H beta. It's at 4,800 angstroms, and the observed wavelengths would be 1.5 times about 5,000, which is about 7,500. So it's also beyond the GRISM we cannot observe at redshift 0.5. There's another emission line, O2. It's a forbidden one, 3727 angstroms, about 4,000. So if we convert it to observed wavelengths, it's about 6,000 angstroms. Am I saying it right? Yes, and we can observe it with GRISM number 7. However, we can observe quasars maybe not at 0.5, but at 0.1 maybe. But can we observe at z equals to 0.1? Since this is our formula that we derived, if we instead plug in 1.1 instead of 1.5, z plus 1, z is 0.1 right now, so it becomes 1.1 here. This term we obtain, how do you calculate it in your head? It's the whole, the 1, plus 0.1, the 10%, so about 7,000. And 10% is easy because you can just delete the last number. So if it is 6,600, 10% is 660. All right, so about 6,500 plus 500, we get about 7,000. It's a little bit more than 7,000 angstroms. So no, we cannot observe the H alpha still at 0.1. We just missed it. It's just outside the GRISM window. But we are sure because we just missed the H alpha, H beta, and O2, we can definitely observe. And this is what I do with these quasars. Those quasars would have to be less than 0.5 redshift in order to observe them with GRISM number 7. Okay, but I can observe other good emission lines, H beta, for example, or O2. Oh yeah, I did a little graphic. How are we gonna do it? Okay, so let's say we have, let's do one emission line first. So let's say we have this emission line, and it used to be in its rest frame here. What happens? Um, no, it used to be, let's say it is H alpha. It is 6,800, close to 7,000. It used to be here. So this is what it means, because with redshift, it starts getting redder. The wavelength increases. So the emission line wavelengths, instead of about 7,000, about 6,500. For H alpha, it becomes 10,000. So it's way out of the window. It went away, it redshifted. But if you had rest frame 4,000, such as the O2 emission line, 3727, I believe, yes, it's about 4,000. Then it moves um, uh, at redshift 0.5. It moves to be about here, 6,000. The observed wavelengths of this emission line, which used to be here in rest frame, now it's observed to be 6,000 angstroms, and it is within our node grism number 7 observing window. So I first calculate my redshift. What is the new redshift? What is the observed wavelengths? What emission lines I need, and then I check which grism I can use, which grism is available that covers that wavelength range. And at this time it was this. I can now do a second. Uh, so here is the original rest frame wavelength, something like this. As this is a rest frame wavelength, but let's say the H alpha is not observed now because it is shifted to 10,000 somewhere here. Um, it's not a very good. This one is not very good because the 6,500 emission line H alpha moves by, what did it move by? It's not a very good visual because it's I have to use a computer, because the way when I move by hand, all of the emission lines are moving with the same wavelength interval, but that's not what happens. The ones, the redder emission lines with higher value for wavelengths, they move a little bit more than with lower value. So this actually a little bit lags behind. So H alpha disappears, we cannot observe it, but these ones we can still observe them in a 6,000 range, 6,500 maybe. What is it for H beta? I have to calculate, because this term here, lambda r, when we look at the observed wavelengths, it depends on the rest frame wavelengths. So depending on whether you have a 6,000 angstrom emission line, you move differently across you increase in wavelengths differently for the observed versus if you have here 2,000 or 3,000. So the shift for H alpha was much larger. It was 3,300. Yeah, 3,500 angstrom difference about, versus for the O2 emission line, the shift was about 2,000 angstrom. So quite a drastic difference. They don't shift with the same difference between lambda observed and lambda rest frame. So the bluer lines move a little bit less. So these blue lines, they also move, but they move a little bit less than these redder lines, such as H alpha. Okay, so this is my discussion about Redshift. Thank you very much. I did it on live YouTube, so I can record a longer term video, but I will post it now online.